Welcome to Curie Electronics. Today we are going to solve 2016 Sdsc Shar Technical Assistant Electronics question paper. Only few question papers are available from Shar. So let's solve this. First question. Which of the following devices use a helix? The answer is TWT. TWT, what is the full form of TWT? Traveling wave tube. It's a microwave amplifier. It's used as a microwave amplifier. And one of the specialty of this TWT is it has got a wide bandwidth. In a rectangular waveguide, the dominant mode is a regular question almost. It is TE10, transverse electric 10 mode. If you see any kind of pipe, so this is how the rectangular waveguides looks. With the increase in frequency, the size of this waveguide, sides, the length and width, it's same only. So it is A. With increase in frequency, the size of the waveguide decreases. Next question. An optical fiber has a core reflective index mu n1 and cladding refractive index n2. Then the numerical aperture is, first of all, the refractive index of core for an optical fiber, a refractive index of core should be greater than cladding. That is N2, that is cladding. So refractive index of core has to be more higher than refractive index of cladding. And numerical aperture means the ability of a optical fiber to collect the light. That is given by the equation square root of n1 square minus n2 square. Ideal bandwidth of an optical fiber is, why do we use optical fiber nowadays? Because it provides very high bandwidth. So it is ideal bandwidth is what we want. Ideally we want everything infinite amount of money, everything. So like that, the bandwidth also we need infinite from the ideal optical fiber. The speech sequence in GSM codec consists of, actually I just googled it. It is pre-emphasis, starting with pre-emphasis and ending with filtering. Pre-emphasis, two are starting with pre-emphasis, that is A and C, ending with filtering. So the answer is option C. Option C is the right answer. So pre-emphasis start and ends with filtering. Now next, let's move to the next question. A thyristor has a maximum allowable junction temperature of 120 degree Celsius and the ambient temperature is 40 degree Celsius. The thermal resistance is 1.6 degree per watt. The maximum allowable internal power dissipation. So every device will have junction temperature. So there is thermal, one equation is there, that is thermal resistance. Thermal resistance. This thermal resistance theta equal to tension temperature minus ambient temperature. Ambient temperature means what? Room temperature upon power dissipated at the junction, that is PD. Now what and all he has given in the question, he has given the, what he has given? He has given the thermal resistance, that is 1.6 degrees Celsius per watt. What is the junction temperature? 120 degrees Celsius minus what is the ambient? 40 degrees Celsius upon PD we have to find. So what is PD? Cross multiplied, PD equals 80 upon 1.6. So 800 I will multiply by 10 upon 16. It is 2 times 10 times. So 100 upon 2, that is equal to 50 watt. So the right answer is option B. Option B is the right answer, 50 watt. So this equation, junction temperature and what is the relation between thermal resistance and junction temperature and the power dissipation and ambient temperature. In the nodal method of circuit analysis based on the nodal method of circuit analysis, you can, I have made some videos on it, you can see. So in nodal analysis we use KCL and Ohm's law. KCL and Ohm's law. Next question. A circuit with a resistor, inductor and capacitor in series is resonant at F0 Hz. F0 is the resonant frequency. If all the components values are doubled, the new resonant frequency is. So what is the resonance frequency equation? 1 upon 2 pi root LC. Now what we are going to do? We are going to double the components values. So what will be the resonance frequency? Let me take it as FR. So 1 upon 2 pi. So inductor value I am going to double, that is 2L. Capacitor value also I am going to double, that is 2C. So which equals 1 upon what I will get? 2 pi square root of 4LC. 4LC. Now what I will do? I will take out this. We will take out the square root of 4. So that is 1 upon 2 multiplied by 2 pi root LC. Now if you see here, for this we have the value. What is the value we have? That is F0. So FR equals 1 upon 2 multiplied by F0. So what is the answer? Answer equal to F0 by 2. This is the way you have to solve it. So the answer is option, which is option? Option C is the right answer. F0 upon 2. The most common method for measurement of low resistance is we use Kelvin's double bridge to measure less than 1 ohm. Usually to measure less than 1 ohm resistance, Kelvin's double bridge. A digital voltmeter has an accuracy of 0.2% of the reading. It reads 500 volts on 1000 volt range. That is, full scale is 1000 volt. What will be the maximum error allowed? Now accuracy as given. What is the accuracy given? What is the accuracy given? That is 0.2%. So if you, without percentage, if you write it, we have to divide by 100, 0.02. So, okay, so what is our scale? We have 1000 volt scale. Okay, this is the scale, full scale. For this full scale, what is the variation in reading, the true reading we are going to get? That is 1000 multiplied by 0.02. So maximum we are going to get 2 volt variation if you use the full scale reading. Up to 1000 volt, if you read, so much variation will come. But we are reading only 500 volt, that is half of 1000 volts. So what will be the maximum error allowed? It is 1 volt is the maximum error allowed. Because we are not reading 1000 volts, we are reading only up to what we are reading? Only 500 volt. For 1000 volt, 2 volt is the maximum error, allowed error. For 500 volt, it is 1 volt. The carrier frequency can be measured by using. It can be measured by spectrum analyzer, frequency counter, mixed oscilloscope. So the answer is all the above. So the answer is all the above. We use this spectrum analyzer to get the detail of the frequency. If you want to analyze detail, the detailed analysis we need, then we use spectrum analyzer. In a p-type silicon sample, the Hall concentration, that is NH. Hall concentration equal to what? Hall concentration equal to 2.25 into 10 to the power 15, minus won't come, per centimeter cube. If the intrinsic carrier concentration is 1 point, so what is intrinsic carrier concentration? Ni. Ni equals 1.5 multiplied by 10 to the power 10 per centimeter cube. Because in a volume we are seeing how many atoms are there. The concentration of the electron concentration we have to find. What you have to find? Ne is the question. So there is a intrinsic carrier concentration, that is Ni square is given as Ne multiplied by NH. Ne multiplied by NH. Intrinsic carrier concentration. Okay, now what is the Ni square? That is, so what we need? Ne we have to find out. So Ne equals Ni square upon NH. NH, okay, NH. So what is the Ni? 1.5 multiplied by 1.5, 10 to the power 20. 10 to the power 10 multiplied by 10 to the power 10 upon what is there in the denominator? NH. 2.25 multiplied by 10 to the power 15. See, 1.5 multiplied by 1.5, it is 2.25, because square of 15 equal to 225. And now 10 to the power 20 divided by 10 to the power 15, that will get 10 to the power 5 per centimeter cube. So the answer is option C, 10 to the power 5 centimeter per cube. When the microcontroller executes some arithmetic operations, the flag bits of which register are affected? It is program status word. The answer is option A, program status word. See, when you add some number, we have to say whether it is overflowing, the answer is overflowing, or whether it is 0, whether it is equal to 0. Based on those arithmetic operations, the microcontroller saves some, set and reset some bits in the program status word. Which kind of multiplexing scheme is adopted by von Neumann architecture, especially for program and data fetching purposes? See, in the von Neumann architecture, we will store the data and the program in the same location. But in Harvard architecture, we will use separate memory for data and program. So in microprocessors, we use time division multiplexing or in microcontrollers. So the answer is option A, time division multiplexing. The correct option for getting x equal to 1 in the given circuit given below is, the output we need 1. How do we get what is the combination of the input? So we know this is an AND gate. So what we need to an AND gate, whenever we give both the inputs 1, at the output we will get 1. So this is also an AND gate, right? For this, what you have to do, A and B has to be 1, then only output we will get 1. So here what is there? A equal to 1, B equal to 1, so that from he will get this 1 we will get. This is a NAND gate. So B already coming 1 here. Then what about C? C has to be 0. If it is both the inputs are 1, NAND gate will give 0, but we need 1. So C equals 0. So what is the right option? A equal to 1, B equal to 1 and C equal to 0. Option B is the right answer. Question number 16. To obtain very high input and output impedance in a feedback amplifier, the topology mostly used is. So we have an amplifier. So we have the output and we are connecting it to a source resistance. Now what is the thing? To obtain very high input impedance, this is the load. And here also we should have a source resistance. Oh, sorry. Let me. This is source resistance, RS. Now the feedback should increase the input resistance as well as the output resistance of the amplifier. So here I have a feedback network. Feedback network, okay. So now RL, we have to sample, okay. We have to sample. We are doing to get high output impedance, we will sample the signal serially. If we sample the signal from the output serially, the output impedance increases. Now we have sampled serially and we have to mix with the input signal. We have to mix with the input signal also serially. So how it is? It is like this. It is not shunt, it is series mixing. Okay. Series mixing. Series mixing and series sampling. Now we will see the options. To obtain very high input impedance and output impedance in a feedback amplifier, for that output has to be current and it should be mixed in series. So the answer is option B, current series. The circuit shown in figure, the input voltage is 1 volt. The output voltage Vout is. So here Vi equal to 1 volt. We are getting 1 volt here. We are giving 1 volt here. So positive terminal of the op amp is, our non-inverting terminal is connected to ground. So it is an inverting amplifier. So what is the output here? This is what is the output here? I'll take it as V01. That is equal to RF minus of RF upon Ri multiplied by V in. What is the value of resistor? Minus 5 kilo ohm. Not minus 5, minus is from the equation. 5 kilo ohm divided by 1 kilo ohm multiplied by, what is the V in? 1 volt. So we will get an output of minus 5 volt, right? So this minus 5 volt we got here, minus 5 volt. Again we are giving it to one more inverting amplifier. So it is a V out. What is V out? A V out equals, again I'll write the same equation, minus RF upon feedback resistor. R in, here what is our R in? This 1K. This 1K multiplied by V in. What is our V in here? That is minus 5 volt. So 6 upon 1 minus is there, correct? Multiplied by V in. What is the V in? We had minus 5 volt from the previous stage. So now what we get? Minus into minus plus. So 5 6 are 30. We'll get 30 volt. So the answer, which is the answer? Answer is option C is the right answer. A class A transformer coupled transistor power amplifier is required to deliver a output of 10 watts. The maximum power rating of the transistor should not be less than. See, the class A amplifier, it consumes maximum power when there is no signal, no input signal. Okay. So what is for a class A transformer coupled amplifier, what is the efficiency? Maximum efficiency it can provide for a class A amplifier? It is 50%. Right. Now what is the equation for an equation of efficiency? Power delivered upon DC power. So here our efficiency is going to be 0.5. 50 because 50%. That is why eta equal to 0.5. What is the power delivered? 10 watt. What is the power consumed when there is no signal, DC power? That is PDC. So we have to find the value of PDC. Then only we should choose a proper power rated transistor. So if you cross multiply, PDC equals 10 upon 0.5, which is equal to 20 watt. So minimum power rating of the transistor has to be 20 watt. This class A amplifier consumes maximum power whenever there is no signal. Question number 19. The relation between alpha and beta is See, alpha value is going to be always less than 1. Okay, you should remember this. It's going to be less than 1. Now, what is the relation between alpha and beta? Beta equals alpha divided by 1 minus alpha. Alpha usually, let us take it as 0.9, alpha equal to 0.9. Then you will get a high value. So this is the equation, relation between alpha and beta, which is the one alpha divided by beta equal to alpha divided by 1 minus alpha. That is, option B is the right answer. Option B is the right answer. Next question. To keep the operating point of a transistor amplifier stable, the following techniques are used. What is the technique we use? It is the stabilization of the operating point. Then the transistor operates in a stable condition. And infrared LED is usually fabricated from, it is gallium arsenic. Gallium arsenic is the right answer. This is for what? IR LED is manufactured from gallium arsenic. And SCR may be turned off. I'm not going in any more because I want to finish almost 25 minutes over. So an SCR may be turned off. How it can be turned off? If you remove the gate pulse from the SCR, it doesn't go off. Reducing the current also doesn't help. The answer is by reducing its anode to cathode voltage. Also, it's a PNPN device. Correct? SCR is a PNPN device. And how many junctions are there? J1, okay, J2, right, J3. 3 junctions are there. 3 junctions. Lisage's patterns can be used to determine. It is used to determine phase shift. In an oscilloscope, we can see this Lisage's pattern when we feed different signals with in phase, out of phase. When they are in phase, we will get a circle. Question number 25. Quality factor in general defined. Quality factor Q equal to omega L upon R. Or this can be written as 2 pi FL upon R. So the answer is option A is the right answer. Question number 26. In a radar system, if the capture area of receiving antenna is A, then the range will be. We will come back to this question. Let's do the next question. Let the maximum range of a radar to be doubled with all other factors remaining constant. The P power must be increased by R max. That is the range maximum of a radar is given by transmitted power, gain of the receiver, transmitter, and then effective area of the receiver, then the target area. The wave should hit and reflect back, that is the target area, upon 4 pi whole square. 4 pi whole square S mean. What is this S mean? When maximum range will get, signal received is minimum. Okay. Now, as per the question, we have to the power 1 by 4 to the power 1 by 4. Now we want to increase the, what we want to do? We want to increase the range of a radar by increasing the transmitted power. That means this much is going to be same. Okay. So what I will do, I will write it as R max, range you have to double it, equal to Pt to the power 1 by 4. The remaining part I will just put it as a constant k, including this power 1 by 4. So it is k. So now what we want, the left hand side double. So we want R max to be doubled. So if I increase the power by 16 times Pt, I will make it as 16 times Pt. Then what happens? Okay, Pt I have increased by 16 times. So now R max equals, what is R max? 16 to the power, I will write 16 to the power 1 by 2 into 1 by 2. Right? I can write it as multiplied by Pt to the power 1 by 4. This is also a constant, we need not worry about it. Now, first this is like, what is that? This means what? 16 square root equal to 4. Again 4 I will take square root. What I will get? 2. That means now this R max has doubled. R max has doubled. We will get 2 times of whatever we are the constant we had. 2 times of k. So the answer is option 16 times. Option C is the right answer. This question I have seen many times, okay, many places. Okay, now, so what was the radar equation, radar range equation? R max equals Pt Gt Ae sigma upon, what was there? 4 pi whole square to S min. Gt is the gain of the receiving antenna. Okay. PTGT, no, gain of the transmitting antenna. Now, we can, instead of GT, we can put the value. Then we will get one more equation, that is PT Ae square sigma upon 4 pi lambda square S min. S min. Now we will go to the question. In a radar system, if the capture area of the receiving antenna is A, then the range will be proportional to. So we have, what is there? Power of 1 by 4 is there. Okay. 1 by 4 is there. Capturing area, that is Ae square, that is, this is the capturing area. Okay. Now we will take the remaining, all are constants. So what we will take? We will take only that R max. But Ae square upon 1 by 4. A is a capturing area. From the equation we will get Ae square. Now what happens to, when you, what is proportional to what? Same way I'll write it. Ae square multiplied to the power 1 by 2 multiplied by 1 by 2. So 1 by 2 and cancels. Now it is square root of A, right? Now it is square root of A. So it is proportional to square root of A. Square root of A is the answer. So you should learn these two equations. And I have this equation we got, instead of what? GT. Instead of GT, we have put the equation of GT and simplified. That's how we will get the next equation. Question number 28. A current carrying conductor is characterized by. A current carrying conductor is what? When a current flows through a conductor, what happens? A magnetic field is developed. Question number 29. In a 100 kHz sinusoidal waveform, the time gap between positive and negative peak of a particular cycle is. So what is the question? 1000. What is time period? Time period only is asking, no? This is 1000 Hertz. So T equal to 1 upon F. 1 upon 1000. So we will get 0.001, that is equal to 1 millisecond. So this is the 1 millisecond is the period of this. From here to here, it is 1 millisecond. 1 millisecond. So what is the question? The time gap between positive and negative peak of a particular cycle. Okay, so the time gap. So from here to here, what is the time? That is the question. So that is going to be half of 1 millisecond, right? That is equal to, correct now. If you look at symmetry is there. So it is half of 1 millisecond. So 1 millisecond upon 2, what you will get? 0.5 millisecond. So if you write it in microsecond, what it is? It is 500 microsecond. So the answer is option C is the right answer. Question number 30. With this, our first part will get over. Then we will do the next part. All of you, if you like the videos, please hit the like button and don't forget to share with your friends. So let's finish the last question. The capacitance of a varactor. Varactor means what? A diode with a capacitor. This is the varactor diode. Here, with what happens? How the capacitance and reverse bias are related? That's the question. Here, if we decrease the reverse bias, capacitance increases. Now, decreases, the capacitance of a capacitor decreases with increase in reverse bias. Okay. So, if we increase the reverse bias, capacitance decreases. So we have completed first 30 questions. The remaining 30 questions we will do it in the second part. Oh, hold on guys, hold on. There's a mistake I have done here, right? It is 1000 kilohertz, right? So 10 to the power 3 is also there. Okay. So it is going to be 1 microsecond. Wait. Let's do it. So it is, okay, let me write it. Here, concept saying, but I not read the question properly. You should read the question properly. So it comes to 1 upon 10 to the power minus 6. 10 to the power 6, right? When it goes up 10 to the power minus 6 second, that means 1 microsecond. So 1 microsecond. So time period equal to 1 microsecond. And half of, what is half of 1 microsecond? That is half of 1 microsecond, 1 by 2. So 0.5 microsecond is the right answer. Sorry guys. So anyway, I saw immediately. So it is okay. We have corrected. It is 0.5 microsecond. So see you soon with the next part.